Hello everyone, hope you all are doing very well. You are all welcome to the third and very last part of our tutorial related to deep learning with satellite imagery. In the first part of our tutorial, we learned how to prepare the satellite imagery dataset and make sure that our dataset is ready, fully prepared for the deep learning process. In the second part, we have used our prepared dataset to build the neural network based deep learning model, and we learn how to perform the training as well as understand the model performance, including prediction as well as the local debugging. And in this third part of our video, we are going to cover various advanced concepts such as remote debugging using third-party MLOps platform. We are using the weights and bias as an example. Next, we will learn how to save and retrieve the models when we are using the custom metrics as well as the custom loss function. Finally, the last part of this video is very interesting, where first we will build an independent model scoring application. We will add the Gradio UI to it. And finally, when everything is working, we will take all of our code which we have developed on local file system or the local runtime, such as your own machine, or you could consider Google Colab, and deploying everything at the Hugging Face space. So creating an standalone application with a Gradio UI and using your trained model performing the prediction. Quite interesting, and there is a lot to learn in this video. So before we start coding, let's take a look in little more detail what we are going to learn in this video. So in this episode of our satellite imagery deep learning training, we start just after the second part of our tutorial where we have completed the full end-to-end deep learning model building as well as the prediction. And in this section, we start our code by learning how to implement the remote debugging, because the local debugging we have already completed in the part 2. So we connect our debugging session with the weights and bias remote debugging, where we create a new project for ourselves to connect the training process which is related to our satellite segmentation imagery, and we connect our runtime environment to this satellite segmentation Dubai images project at weights and bias, and push all of our logs directly from our training process through this callback. During a very small 10 epochs training, all the logs has been pushed from local file system to weights and bias projects. Here, system specific parameters, whole model details, as well as the logs, including our all the artifacts files with the model. After we complete the remote debugging, the next step for us is to learn how to save the model and reload the model. And because in our project we are using custom loss as well as the custom metrics, we are using the Jaccard coefficient, and our custom loss is the total loss. So the model saving and model loading is little different. So in this second part of this particular video, we learn how to save the model and how to load the model by passing the proper custom objects specific to our loss and the Jaccard coefficient matrix. And then we perform the prediction by using the loaded model which we have saved. In the part 3 of the same tutorial, we learn how to collect the activation and the gradients related to our prediction process. Once we perform the prediction with our deep learning model, for every layer, we could generate how the input image is processed at each layer, and we learn that for every layer, how activation as well as the gradients output is generated, including the heat map. And all of these images are stored in this activation as well as the heat map folder, where we read these images specific to each layer processing and learn how these images are generated and the process behind it. And in the part 4, we actually learn to build the complete Gradio UI at the Google Colab first. So this is the full code we write from scratch. So after we build the Gradio UI in Google Colab, we launch it, we validate that we could perform the prediction using the model which we have saved locally. We could get the mask output generated from our model based on the models which we have saved, this satellite imagery.h5. And at this point, we decide to go to Hugging Face and create a new space named satellite segmentation prediction. And we build this code app.py, exact same code which we have generated in Google Colab. And finally, with few tweaks needed, we make sure our space is running and this app is ready to perform prediction exactly. It was working in the local Google Colab environment, and we take the same image, we run it, and we generate the same prediction at the Hugging Face. So this tutorial is a combination of various advanced methods which you have to know just after learning how to process your input data and generating your deep learning model. So the content which we are covering in this video is a complementary topic and advanced in nature to help you learn and extend your knowledge specific to building deep learning model and deploy them, debug them, troubleshoot them. And by completing this exercise, you actually complete end-to-end machine learning life cycle, all the way from data processing to the model deployment and several steps in between. So in this step, our objective is to perform the training, and when the training is happening, the training logs are going to be shipped to a third-party machine learning model deployment or model training process. And in this scenario, we are going to use the weights and biases, where you could actually sign up a free account, and we need to create a project. So first I will create the satellite segmentation, and we just call it Dubai images. So that's our project, and let's create the project, because this is the project which is going to collect the logs related with our application. And our project, currently we are using Keras, so that's why we have selected Keras, because the quick start guide is already giving you details that how you are going to connect your runtime environment to weights and bias server. We are here, and it is the place where we have left off. I have made this training only 10 steps. Our objective is just to run these 10 steps, and when this training is happening, the logs are going to be visible here. So first thing first, we can just follow the quick start. We need to make sure that we have weights and biases library installed, and create a new cell here, and you can check pip show weights and biases. It's not there. It means it's time to install. After the installation is done, we need to make sure that we log in it. Basically, login means that you are connecting this environment to this environment through a token. So let's here, and then we will be using command as a weights and bias login. You see, it's asking for API key, and we are running a command here. So that is a terminal command, and key is already visible here. So I will be copying the key and pasting here, enter. And as you could see that our session is connected. At this point, we have our runtime connected with the weights and bias runtime environment. Now we will take this code. That's where the training is happening. I'm going to create a new cell, and I will be separating these two lines of code. So first we are importing the weights and bias, then we are importing this weights and bias callback method, which is related to cateras, needs to be connected from runtime environment from Google all the way to weights and bias. Now we are going to initialize the weights and bias runtime environment, and this is a project name. So this runtime environment, when the initialization will happen, that will give us hook to this project which we have just created here. So let's initialize it. Entity is a Prodramp because that's the account name, and the satellite segmentation Dubai image is the project which we have just created. And there is some warning, so we can use this command, which is the message came to us. Open a new cell, use the command weights and bias, login, relogin, and it needs the key. So key is here. I will be copying this key again, pasting here. Let's run. If you run weights and bias command on the cell, you see the different options. So initializer, which we have ran earlier, and here is the status. So always use the status command to see. Here is our some of the information related to weights and bias connection. I'm reinitializing the project actually. So after we have successfully logged in here, some of the data related to our project, if you see here, weights and bias folder was created, and logs related with runtime is going to be stored here, and then they will be pushed from here to here. So connection is there. Now we need to connect the callback, the weights and bias callback with our runtime. So this is the callback. And if you remember in the part 2 of our tutorial, we have used the callback method to connect with local debugging. But now we are not performing the local debugging. We are performing the remote debugging by using the weights and bias. So that's the callback we are going to enable, and we are going to connect with the callback related with our segmentation project. So now we are going to take this weights and bias callback, and we are going to connect here with this callback. This is the method. Let's run it. So first epoch is started. So the first epoch is going to generate the steps based on our batch size. So that's all we have already talked about. Now we can come back, look into, this is the latest runtime. That is what being synced here. Let's come back to info. So it's running, and we can look into the run. Now the accuracy loss, validation loss, epoch, you see the Jacquard coefficient has already been added, and the validation Jacquard. So we haven't even set any of the parameter that what we want. By default, weights and bias figure it out that this model which is being set to run already has some of these parameters which is being set earlier. So here you could see that we are using these metrics. So everything what has been configured earlier, which will be pushed. This is how you are going to save your runtime environment from wherever you are running to weights and bias. Runtime environment related to with this particular run has been saved these monitors. So these are the logs related with this run. That is exactly what you have seen here. So that logs are being pushed into. Here are the files. So all the files, and here is your model, which is about 23 meg model has already been pushed also. So the good thing of using any of the systems such as weights and bias, it actually automatically collect and back up your runtime statistics to the server where everything is persisted. So in the next run, let's try to save some of more parameters. So this is where our run is. So we can come here, write some of the logging. So for example, we could say that weights and bias dot log, and here we could say the accuracy is our Jacquard coefficient. Then we can also say the loss is our total loss. Then if we would want to connect the configuration, so for example, we could say weights and bias. In the configuration, you could say that our dropout is 0.2. So we are initializing. So we are going to get a new run because this initialization will give us a new run. So we got a new run, aardvark 5. So now we are getting a new run, which is the devoted feather 6, and you see that accuracy and loss is only being sent because we have exclusively mentioned that please only collect accuracy as a Jaccard coefficient and the loss as a validation loss. After the run, the files are being saved. Model has been updated. If you would want to download this model, you can download it, and model will be downloaded from weights and bias environment to your local file system. There is a lot you could do, but our objective was just to give you an idea in this workshop that how you could take your runtime environment in Google Colab or wherever you are running, and by installing the weights and bias packages and libraries, you can have all that runtime log, model, files, etc. can be pushed from local file system to your runtime. So now I will just go ahead and export this Jupyter notebook to DeepWorks repo, file, save, and we just call it weights and bias. So now this Jupyter notebook has been pushed and it's accessible for anybody located here. In this part of our video, we are going to learn how to save the model with all the custom metrics which we have created, and we should be able to reload the model. So this is the model which I have just completed the training with 100 epochs. It should be a better performant model comparatively. And here we could perform the prediction with some random test images. So this is the predicted image, so it's good. So now we need to save the model. So here is the model configuration which we have trained earlier. So I will comment it because we do not need to see the log message. So now we need to save this model. We will try to save the model and reload the model and see that if the method which we are using to save the model is correct. So now we will say model.save, and here we will provide where we would want to save the models. We could say satellite imagery.h5. That's our model, and this model is going to be saved into this folder. So let's save it, and if we say ls-lah, model will be saved here. We just need to go back and reload this folder because it isn't refreshed by itself. So here is our model here. It's about 23 meg. Now we are going to load the model, and in order to load the model, we can use the Keras library because this is the Keras model. So we could say from keras.model import load model. So that's the method which we are going to use here, and we could say saved model equals to. That's what is going to be our model. So we could say we need to load the model, and we will provide the path. So that is the path. So it should be the content and the model name. Let's load it, and it tells us that the loss function which we have created. So remember, we do have the custom loss function which we need to make sure that we have to add that into the custom objects. So in the load model, there is a parameter called the custom objects, as you could see here. So let's take the custom objects, comma, and in the custom objects, we need to provide the custom objects. So we have the loss method. So our loss method is loss equals to, and that should be the JSON, and we need to provide the total loss. So that is our loss method for the custom objects, and that's, I think it's much clear now. Custom objects. Let's see what happens. Now the error is unknown loss function. It means that somewhere this loss function name is actually not the loss or something like that. We can figure it out by looking into our model. So first you say, what is our model? This is our model object. Then you look for model.loss class, and then you define the parameter. So there is a loss name, and here you find the loss name. So even when in one second here, when our loss is equal to total loss, so this loss parameter is part of compile method. However, when this total loss function was used as a loss function for compile, the internal name for loss function was different, and that is what we have seen here at the very bottom and its name is this. It means we need to take this loss name and then we need to say that in the custom objects, that is our loss method. And now if we run it, let's see what happens. Let's see. So now it says that unknown metric. So it means that our loss is accepted. Now we need to provide the metric. So we already know that we have a Jacquard coefficient, which is our metric. So here we say comma, and the Jacquard coefficient equals to Jacquard coefficient. So these two values are part of our custom objects that we need to provide in order to load this model which we have saved. It means that if you are using a total new Jupyter notebook, a total new Python runtime, and you would want to use this model which we have saved and downloaded to our local file system, such as this, or we have used weights and bias where we have seen that our model was uploaded here, in any scenario, we would have to use the particular loss method as well as the Jacquard coefficients to use this model. So that is our saved model. If we run it, looks good. I think our saved model is good. And now if you look into the saved model, and again, it's the same model which we have saved. You can say get config, same configuration. So now it's a saved model, and now we are going to use this same model to perform the prediction. We can come here where the prediction was happening here. So we can validate that if we replace this model with saved model, the prediction should be working as expected. So I'm going to just run this code one more time, which is using the model. So this model is already used for prediction. Everything looks good. Now I will replace this model with saved model. So let me take this line, keep it, and saved model is used here. Run this code. Now the prediction is collected based on saved model. Let's run this code. And there you go. It means that this is the predicted image. So the way we have saved and loaded our model, that method is all correct. So let me comment this part. And I have already saved this model as satellite imagery to the local file system because this is the model we are going to deploy at Hugging Face. So now in our next step, we need to use a custom image and we need to make sure can we use our model to perform the prediction. So let's create a new section called, so that's the third section we would want to learn next. So I have uploaded these two images, FC image 1, FC image 2, and these two images are the one which we would want to use our saved model or the model which we have created just in this tutorial to perform the prediction. So let's take a look how these images really look like. So we could say image.open and content fc-img1.jpg, and we could say plt.im show. So this is the one image, and we could also see the second image. So these are the images which are my neighborhood. I live very close, so I live Foster City, and these are the images where we could see the water area. This is the lagoon, and here is the bay, San Francisco Bay. It hits to San Mateo Bay. So this is the bay water. It is the lagoon water. Here is the road, some building structure, and there is a lot vegetation area. So I think these two images are going to be very good images in order to perform the prediction. So let's take image is equal to image.open. So we have loaded this image. Now image is equal to image.resize, and if you remember, all of our images were size 256 by 256. Let's use resize. Now we need to take this image and we need to convert to numpy array. So you can say np.array, and then you can pass this image. So now this image is actually the numpy array. In the next step, let's expand the dimension. So we need to say image is equal to np.expand dimension, and we need to pass the same image, x is 0. So now we have expanded dimension image, and I'm just getting help from here. So if you see here that was these are our test images, and we are taking the test image. So these are all the numpy array. That's why I already know that numpy array. So here we need to expand it. Now this is our input, and now we could perform the prediction. So at this point, if we take this image and pass it and see if prediction can be collected. Prediction is create the predicted image. So if this is the predicted image, use this same method to perform the prediction. So we do not have the matched image, so we could actually remove this part. So this is our predicted image, and the original image is going to be the actually it's being changed, so I will convert that back to this. Let's see. And that was the prediction based on this image. If we use the FC1 prediction, FC1. So at least we could say that using a custom image, we are able to perform the prediction. And now it's about how good and how performant your model is. But looking into these results, we can say that definitely our model is being applied to perform the prediction on this given image. So let's export this Jupyter notebook to GitHub. So I have added this tag save load model in this notebook. So this Jupyter notebook is available at GitHub, and at the very bottom here it has a whole instruction about how to save and reload the model with the custom loss metrics as well as the loss function, and it also has the code to performing the prediction using the custom image. So in the previous step, we have seen that how we could use a custom image to perform the prediction. Now we are going to use the same method and learn how we could generate the activation as well as the gradients output. For that reason, we need to install this library called the KERACT, which means the Keras activation. So let's make sure that we could install this library. So pip installed Keras activation. So this library version 4.5.1 is being installed. We can always look into the setup.py. You could see this is the version 4.5.1. So this means this correct one. Let's import this. So import KERACT as K, just simple. Now once we have K, it has these different methods available, and the method which we are most interested is get activation as well as the display activation. So let's perform the get activation, and the get activation is going to take the model. Then we need to provide along with model, we need to provide the input image and few other parameters, but I think that is not needed as of now. So we could say our model in this scenario is this saved model which we have loaded from the disk. First we saved, then we loaded successfully. So that will be our model. In the next step is our image. So our image we were using, this is the predicted image. So our source image is this, which we have loaded here, FCIMG1. So that is our input. And in the next step, we need to nodes to evaluate. We can say right now is none. So let's go ahead without none. Next, we need to say output format. And output format is default, it's simple. So we could actually provide just keep the simple right now. And auto compile is true by default. So we will keep it as it is. So the result of this get activations will be saved into a particular object we call activations. So that's where the activations are here. Let's run it. So this is the activation. Get activation has ran and generated the activation output, but it may not be useful just to see the number. We need to apply these activations on our result. So let's go ahead and perform the activation result collection by using the display activations method. So in order to save the activation, we need a particular folder. So in the content, we will create a new folder. We call it activations, and ls-lah, the path is going to be the content and activations, so it's empty. So this path where the activation data is going to be saved, ke dot display activations, because now we have collected the activations. So display activations, and now we need to pass the activation, and then cmap is going to be where it is. So save is true, it means save all that data to true, and we need to provide which directory, and directory is going to be the this one where we have just created the folder, and I think that's what is really needed. Let's run this. And now what's happening is that all that activation details which has been collected first, and now we are generating the activation, and looking into the activation, you will see that based on our input image, as we were performing the prediction step by step, this result was generated. So in order to understand, we need to have a full understanding of our model, and for that we can look into the Netron. In the Netron, the satellite imagery H5, and open here. So this is the model. So if you look into our model in detail and looking into our output, let me close it here. As you could see that these are the different layers based on our input image has been applied, and our activation results are generated. They are all stored here. So we need to display all of these images in order to understand the result. So all these images has been generated based on this output. So total 40 images are generated, and if we look into and calculate the number of layers in this deep learning model, each of these images represent the way how the input image has been processed. So let's say first two images. So here the first image is 0 underscore input underscore 1 dot png. And if we look into convolution 2D, and if we open the very last image, which is the 40th, 18, 2D underscore 18, and that's where the predicted image is, which is representing this image. So you can get an idea that between the very first image and the very last image, all of these images are going to show you that how this model was used from input all the way to this output convolution to 18. So that's why you see this 18, number 18 is what the result of this very last, versus the input layer, very first one is 0 input 1, is actually representing the 0 input 1. If you would want to see at any level what was the output, you can just select that particular layer that can help you see the output. So the objective what we had to see the activation results by using Keras activation library, explanation should be enough for you to get yourself started. The more you would want to learn about the activation, my suggestion would be to just go look into this library explanation as well as the various examples available. They are going to help you a lot in order to understand the results. Along with the activation, the same library also has the heat map, which we can get k dot display heat map, and display heat map method can actually take the activation result. So we need to pass the activation. So activations will be this activation value. So this is our activations. That's the activations. Then we need to provide the image. So image is our input image. We need to just make sure that image must be the numpy array. So that is our image, and save is equals to true, and that we just call it, this is the heat map. Image is equal to image. Let's run it. So actually let's remove this guy. Okay, and image, that's where, and let's run it. So let me take this image, which is the source image, and we have, oh, we should not, because right now the image is already expanded, so we need to provide this np array image only. So for that reason I will just use here source image and image as array, and that image has to be fed to here. So looks like this error converts 0255 image to be 0 to 1. So looks like it's input image divided by 255.0. So I believe is that we can take this image as array, and we can go and say that as type and set it up numpy dot float 32, and that's what we could pass image as array. And we can also look into this, and there is a directory, so we need to save that heat map. So I will create a folder called heat map here, and all that data should be saved into the directory as content/heatmap. Now let's run it. So for every layer, now the heat map is going to be generated. We can look into a particular image, and as you could see, this is the heat map look like. Then second image, third. So you are getting a better understanding of how the input image is being processed through the heat map view. And for every layer, as you could see here, you are going to get the heat map. So now all the heat maps are generated for every layer, and this folder heat map has all those heat maps. Now we can go look into the very last one, 40th. If you see in terms of heat map, there is a one color patch of this and then other color patch of that. Between these two, you could see a clear difference between the color patch, and looking into the result, you can also validate that this is what the color patch really look like based on predicted image, and that was the very last heat map for the given image. So there is a lot you could go deep into and learn from these activation heat maps as well as the activation output. But for the sake of time and this workshop, my objective was to show you that there is a lots of things you could learn by using a certain library. So you can look into these various examples available in this KERACT or Correct library, and that should be able to give you a very good start, and it's depending on how much time you would want to invest to learn deep into it. So before we go, let's export this notebook to our GitHub. I have added the tag name activation heatmap and export it. Notebook, at the very bottom we should be able to see these images. So here are the activation output, and here are the heat map images. So now you can use these Jupyter Notebook and expand your knowledge and experiment as you would want to further continue. So in this step, our objective is to build the just prediction application first at Google Colab. And once that application is ready, then we need to add the Gradio UI on top of it, and finally deploy that whole application to Hugging Face spaces. So first, we need to take the code from this Jupyter Notebook, which was fully working, and export some of the code here. So we need these libraries just to start with. So these are the libraries we need, and we will remove some of the code which we do not need. And we actually need the segmentation model installation. Reason we need is because that is what help us to build the loss function, because that's where we use the segmentation model. So let's take this, use that, and in order to make it work, we have to install the segmentation model. In the next step, we are going to use some of these libraries because we need to build the Jacquard coefficient. So Jacquard coefficient use the Keras backend. This is what is used to generate the total loss. So that's the total loss. Now we need code to load the model. So let's use here the Keras load model. We need to make sure that the model is available wherever we want. So the total loss we need to make sure is there. Jacquard coefficient is there, the definition of that. So that will help us to load the model. Once this model is available wherever we would want to run this code, then the performing the prediction, we need to make sure the images are there. This is our image reader code, which reads an image and return the image which we would want to perform the prediction, and that's where the prediction is. And we just called it satellite model, and that is what we are using here. That's the prediction part. That's where we are defining, creating the predicted image, and this is how we are showing the predicted results. So some of the code we have taken here. Now I will go ahead and I will disconnect this Jupyter notebook, and I will connect this Jupyter notebook in Google Colab, and we call it satellite segmentation prediction. That's our library. And let's see, first we need to install this because that is needed. It is installed. Now pre-processing, we haven't used it, so I think these are the libraries we needed. Then Keras is specific. Now define the Jacquard coefficient. Let's see if we could get the total loss. Now we need to make sure that we have this model which is in this section. So let me go and upload the model from my local file system to here. So this model is being uploaded from my local file system to here, and that should be visible here. Then after, I need to make sure I can upload these two images at least to get us going. And once we made sure that this code is working, then we can write a Gradio UI on top of it. So our model is uploaded here. We could load the model. If we check the satellite model dot get config, we should be able to get the configuration. That's very good. Let's comment it. We don't need all that output flooding our cell. Now we need to upload these two images. So the images are uploaded. Let's load the image, perform the prediction, and see the output. There are the results. So just looking into this code, you can get an idea that this is all code we really need in order to perform the prediction. And we have extracted all that code from our one of the Jupyter notebook, which we have used to train the model and finally use for prediction, as well as we have done tons of things in it. So we really do not need any of this. So now I will go ahead and close this tab. We don't really need it, and everything we have covered is already uploaded to this folder. All these Jupyter notebooks, based on all the work we have done, they are all uploaded here. So now only thing is really needed is this one. So this is just a prediction code. We can save this Jupyter notebook as a base prediction, and then we can create a new code on top of it, and we call it GUI. So let's rename as base. So the base prediction code is all here. Everything is good to go. Now we need to build the Gradio base UI so that we can just upload an image, and that image and the predicted image will be visible on its side. So we need to import the Gradio here. So let's see, Gradio is not here, so we need to install it. Let's go top. Gradio is installed. It means we could import this Gradio library. Now I have already lots of code available at the Hugging Face. Some of these samples, like if you would want to learn how to create the multi-tabbed UI like this, I have a whole YouTube video, so you can learn how to create this multi-tab UI. So we just really need to create an UI, something like that. You drop an image here and you will get an output here. So very simple code we just need, that's it. But only this tab we need to build. Select your image. You can get the code all in this app file as well as the second file, which is the image process UI, which is a class, and there is a lots of code. But in order to make it work, we just really need to build a very simple UI based on Gradio. So I will just show you how you could build it. So first you need to get the starter code, which is here. So you have Gradio. So you need to get the blocks, and that this is what object you are going to use to build the UI. So let's come back here. Your app is the blocks. So GR blocks. Now based on that, you can build your UI code. And because this my apps is being passed into here as a parameter to this image process UI class, and this object is self UI object, and that's where it is. So actually I will take this whole code, and we just really need the very first tab that will expedite our coding. And now we need to activate this whole UI, and the activation is here, self UI launch. So we need to launch this. So you could say my app dot launch, and that's where your Gradio UI is here. And if you try to click on first, the UI is visible here. You can drop an image, because remember, we haven't created the backend code to handle this UI. Like when the image loader happen, how everything is going to process, nothing is there. However, this is the dummy UI. You could see, you can drop an image, nothing is going to happen. So now that all code, we really need to add it. And you can also click this link, which will open the UI in this tab, fully functional UI. So let's come back here and write more code to it. Let me fix this indentation. When the image is processed, we need to perform source image, whatever click happens. So this is our button. So you will come here, dot click. So that is your click event, and click event has three things. First, you need a function. So we need to define a function here. We call define process input image, and that is what is going to take the image as an input here. So let's just right now call it return false. So at least we could use this as an input. Then we need the input parameter, and then we need the output parameter. So input parameter is the image source, output parameter is the image output, and we can also use the labels. It means that we need to send a text and the image out. So here we need to provide some of the message and output, just to make sure our method is correct. And if somebody who is very new, doesn't really have experience with Gradio, please check out my few videos where I have explained a lot about how you could start from scratch and be expert in Gradio. So that is our method. So for example, whatever your image source is the input, you can return as input, and you can write output. So whatever we are sending as an input became the output. Let's run this code. And now you can run this code again, launch. We have loaded the image. If we click on here, the image should be processed and it should be visible here, and that's where you go. So the click event happened. This image was uploaded from local file system to backend, and backend processed here. So if we write our prediction code here, the predicted mask image should be available here. We just really need to process this input image. So the way we process this image, we do this processing. So we take the image, we resize it. So this became the image, became the image source. Resize happened. Then after we perform the prediction. This is the prediction code, and we take the prediction, we generate the predicted image. That's the predicted image, and predicted image is actually the output. Right now we could say the predicted masked image. So that's our method. Let's run this, Run this, and that's gonna launch our Gradio app. Let's drop one image here. Run. Error. Take a look into the error. We have debug information, so cannot resize an array that reference or is referenced by another array. Okay, you need to understand a few things before we will be able to get this whole Gradio thing working. So when we are reading an image, first thing we resize that image to 256 by 256. Then we convert that image to NumPy array, we expand the dimension, and that expanded dimension image is what fed into the model.predict. And when the prediction come out, the prediction is image which we actually render it. And the matplotlib library render that mask image output. So it means that whenever we are going to get the image, first, I already know that whenever Gradio is sending the image, that is actually not the image type, it's a NumPy ND array. That's why resize cannot happen, because the resize is a method which is applicable to the image type, not the NumPy array. So we could not use this method, and it means that we do not really need to convert an array. So we do not need these two lines. Let me comment this one here. So when the image comes, immediate we need to expand its dimension. So that is right. The only thing we need to make sure is that the image which we are feeding has the size of 256 by 256. And what I have done is that I have added the shape here. So whenever the image is being read, it's automatically reads the image of the size 256 by 256. So you have two options. Either you convert this image array to image, then resize it and everything you do, but we do not really need everything because we have set this shape. So when the image is going to be read by the Gradio, it's automatically converted into 256 by 256. And that's what we are getting here. So that way we will get our image out, and at this point we will get out image will be fed here, and that's where the prediction is going to come. So now we could run. Once the Gradio app is started, let's drop the image now. It's black. At least output is there, but it's black. Let's understand what is going on. Let me stop it. So this is the predicted image. What you can do, you can actually print this image in output, and that will help us understand what is going on. So we can run. Image prediction has started, black image, but the output is important. So you see here that these values are right now 1, 2, 3, 4, 5, 6. So these are the values we have seen, like because of 6 label. So when this image is being sent to Gradio, this is actually being considered as a 0 to 255 number. So it means that 1, 2, 3, everything is looks like the black. That's why this image is actually look like the black even when the mask has been created for that image. I was using a different image, so let's use this image. That's the image, and if we look into predicted image, so this is the output, but we are seeing everything black. Let's look into the result. This is what we are seeing, 1, 3, 1, 3, these values, because we have asked this method to print. That is being printed here 2 times. So this is the newer image. So 1, 2, 3. So one option is that if you take this output, a predicted image, and you multiply with a number to get 250 values, you could actually multiply it by 50. So if we take this value, and we could say that this equals to multiplied by 50, and let's stop this. Run. Start the prediction, and there you go. So you get an idea that this is exactly the output. What we are seeing here is the same as here. The only difference is that whenever we are using the matplotlib, it actually colors it itself. However, here we have to do everything manually. But that is exactly the result you are seeing in the prediction, just a little bit here and there. So you get an idea that this is how you will be able to generate the results back to your original image. So that's all. It means we do not need these lines, sorry, and we can actually remove this part from here, and that is what we have used depending on the number of the values we are seeing 0 to 5 for 6 labels. So for that reason I have used that, and based on that we could generate our output. First I will go ahead and I will take this code and I will export it to the DeepWorks. So I will call it Gradio UI. So we have added Gradio UI. So this shows that it has the Gradio UI related code. That's good. Now in this next step, we will go ahead and we will deploy this code to Hugging Face. And we also need this model to be deployed. So let's come to Hugging Face, space, create new space. We call it license. So that's the MIT license, and it's going to use the, it's a public and its UI is built based on Gradio. Create space, just come here, create a new file, and we just call it app.py. Then this is our import, then this is our second piece of import, that's our third piece of import. Then we are building the Jaccard coefficient. Then we are generating the total loss. This is how we are loading our satellite model. We can create a folder called the model, and then we can save that model there. So we need to make sure the model folder is created, and rest of the code is this. Okay. Next, this is to perform prediction, which we are not using. We need to go this method, which perform the prediction. Then here is our Gradio code. This, and launcher. Created the app.py. That's our app.py. Now we need to create model. So model slash model info txt, and here we can just provide that this model is created using the code from this repo. Let's commit it. So now we have model, and now we can upload a file here. So there is upload files in this folder, and model is going to be added here. So we are uploading this 24 meg models from my local file system to Hugging Face repo. Okay, so model is available in the model folder. Now we need to come back our files area, and we need to add file called requirements.txt, and we need to make sure that this requirement is satisfied. OpenCV Python. So now we are getting the runtime error. It means the build errors are passed. We are having problem with the runtime error. apps.py, everything seems okay at this point. Status is running. We can come back to app mode, At this point, our app is up and running. There are no more any problems. We can drop the image. We have used this image. We can run our model and see, and here are the masks. Our objective was to first build the Gradio UI, which we have built Google Colab. Then we have deployed our whole application here, and all that application code is in app.py in this files and version section. And here is your GUI. So that's all I wanted to show you. And our objective related with creating the Gradio UI has been completed. So that's where we are going to complete this third part of our tutorial video, as well as the complete 3 series of deep learning for the satellite imagery dataset. I hope you have learned a lot. If you have any comment, any feedback, please do write so, and I will be happy to learn from it and progress forward. Once again, thank you so much for your time. I do appreciate it sincerely, and I'm looking forward to seeing you in my next video. Until then, thank you so much.